Hey everyone, and welcome. Today, we're jumping into a really powerful little trick for solving a very specific type of trig equation. It's called the square root method, and it's going to make your life a whole lot easier. So let's get right into it. Right off the bat, take a look at this equation on your screen. How would you even start to solve this for theta? The most important thing to notice here is that the sine function is squared. You see that little exponent? That's the key. That little 2 is our clue, and it tells us exactly what strategy we need to use. And that brings us to our first idea, recognizing the squared trig problem. Because honestly, with trigonometry, knowing when to use a tool is just as important as knowing how to use it. Okay, so check this out. This slide makes it super clear. On the left, we've got our target for today. It has a squared term, that's sine squared, but notice, there's no regular plain old sine theta term. That's our green light. That's when we use the square root method. But now look at the equation on the right. It has both. It's got the squared term and the linear term. Whoa, that's a different beast entirely, and it needs a different tool, factoring, which, don't worry, we'll cover later. All right, so now that we know exactly what kind of problem we're looking for, let's break down the how. And the great news is, this is a super straightforward, repeatable 3-step process. You'll have it down in no time. And here they are. Step 1, get that squared trig function all by itself, isolated. Step 2, hit both sides with a square root. And, this is the big one, you cannot forget this, you have to include the plus or minus symbol. So important. Step 3, now you've got 2 much easier equations to deal with. Just solve them. So let's talk about that little plus or minus symbol for a sec, because it is everything. Why is it such a big deal? Well, think about it, right? If you square positive 2, you get 4. If you square negative 2, you also get 4. The act of squaring completely erases the original sign. It's gone. So when we go backwards, when we take the square root, we have to put both possibilities back on the table. Forgetting that plus or minus means you are literally throwing away half of your potential answers. Okay, theory is great and all, but the best way to really get this is to see it work. So let's dive into some examples and walk through this process together step by step. Let's circle all the way back to that very first problem I showed you. We're going to solve 4 sine squared theta minus 3 equals 0 for all the angles on one full spin of the unit circle, from 0 all the way to 2 pi. So, following our recipe, step 1 is to isolate. We'll add 3 to both sides, and then we'll divide by 4. Simple, clean algebra. And boom, just like that, we have sine squared theta equals 3/4. The squared term is officially all by itself. And now for the big move, step 2. We take the square root of both sides. The square root of sine squared is just sine. The square root of 3/4 is the square root of 3/2. And most importantly, we remember to slap that plus or minus symbol right out front. And this is why that symbol is so cool. Our one equation now splits into 2 separate little puzzles. First puzzle. Where on the unit circle does sine equal positive root 3/2? Well, that happens up in quadrants 1 and 2 at pi/3 and 2 pi/3. Second puzzle. Where does sine equal negative root 3/2? That's down in quadrants 3 and 4 at 4 pi/3 and 5 pi/3. And look at that, 4 distinct solutions. But, what happens when the math leads you to a dead end? Let's look at a no-solution case. This is super important for understanding the limits of this whole method. We need to solve cos square theta plus 1 equals 0. We follow the exact same first step. Isolate the squared term. We just subtract 1 from both sides, and immediately we hit a wall. The equation becomes cosine squared theta equals -1. And that right there should set off some alarm bells in your head. And why is that a problem? Because of this fundamental rule of real numbers. When you square any real number, doesn't matter if it's positive or negative, the result is always positive or 0. It can never ever be negative. So an equation that says a squared value is equal to -1, that's a mathematical impossibility. There is no real solution here. Game over. This brings us to the single biggest, most common mistake students make with this method. It's such an easy trap to fall into, but I promise, once you see it, you'll know how to avoid it every single time. Just look at this slide. On the left is the mistake, completely forgetting the negative root. If you just solve for the positive case, yeah, you'll find 2 correct answers, but you'll completely miss the other 2. The correct method on the right, using the plus or minus, makes sure you find all 4 valid solutions. On a test, that's literally the difference between getting 50% and 100%. Okay, so you get it for class, you get it for a test. But why does any of this actually matter outside of a math textbook? Let's connect this abstract process to a very real, very solid application. And this is where it gets really cool. In structural engineering, when people are analyzing all the complex forces acting on a bridge, they use vectors. And often the math boils down to equations with squared trig functions, just like we've been solving. Finding theta helps them figure out the precise, perfect angles for beams and supports. And here's the crucial part. Both the positive and the negative roots from the math correspond to real, physical directions for those forces. Getting this right isn't just for a grade. It's essential for building things that are safe and don't fall down. So the key takeaway is this. The square root method is your go-to tool when you see a squared trig function all by itself, with no linear term. Which, of course, leaves us with one final, hanging question. What do you do when both of them are in the equation? Well, we'll just have to tackle that next time.